Let's rock and roll. Right. Yep. It's a big lesson. Photons. You can write that down, please.
New lesson.
Yes, Jerry. New lesson.
Oh.
Indeed. Right. You got that?
Yeah.
That's trust me. It's boring stuff. Right. Photons. Yeah, there's a lot to do. There is a lot to do. Yeah. A quantum, or quanta, is the minimum amount of a physical entity that's possible. So in other words, what exactly does quantum mean? Basically means the minimum amount you can have. So, for example...
Energy.
No, not just energy. Anything, actually.
Anything. So
Not too far off. It's the physics at the smallest scale possible. Less than nano. Yeah. In fact, it doesn't really become interesting until 10 to the minus 10. So, quantum means a minimum amount that is possible. For example, a simple example. When you're talking about people, you can only really have as one person, as the smallest group.
No, you
people. You can't. That's still a person, though. Yeah. Anyways, continuing. Do you have this? Yeah. Now, in fact, so far we had no need for quanta. I mean, we didn't need it. For example, we don't have a quanta of distance. You know, we can have 1 meter. I mean, there's no minimum distance. We could have like 1 meter, half a meter, a millimeter. You could have 10 to the minus 10, minus 11, minus 12. There is no minimum distance. So, what do we need it for? Well, we need it for this thing called a photon. You see, what a photon actually is a single quantum of light. In other words, it's the smallest amount of light you can have, and any less, you would have nothing. So it's like a minimum amount of light, and you can't have less than this. So a single quantum of light is also called a light quantum, and it's just one piece of light. You know, it's like, that's it. Any less and you have no light. It's the smallest unit of light. It's called a photon. That is okay, I forgive you. But what was your question? Dichrome would mean 2 colors. We're just talking about...
Is it like monochromatic? One light.
Well, monochromatic means 1 color, that's fine. But a photon means the smallest amount you can have. Like, imagine you turn the light on, and you have light coming out, and then you turn it off. But then you turn it on again, and then you turn it off quicker. So you just, you really want to make a small amount of light to come out. The question is there a minimum? Like, for example, if you turn the light on and then off, so quickly can you get no light? Is there like some point at which you can only have this light or no light? So there is. You can't make the light as small as you want. There is a minimum amount of light, and if you try to make less light than this, then you don't have any light. It's a bit like in electrons, you have orbits, and there's a minimum orbit. What's this one called? The S orbital, isn't it? S1 or something, isn't it? Can you put it in an orbit lower than this? No, you can't.
Flying around.
No, you can't. If you try to put it in an orbit lower than S1, then it won't enter any orbit. It's the same idea as that. Yeah.
Well, isn't it like energy, like light is before.
Yeah.
Where is one particle of light?
It's the smallest amount of light you can have, and then you can't make any less than this. It's like the minimum amount of a wave, you know.
If you can count it, then it has a shape. So it isn't energy.
No. You could count how many photons you have. It'd be a big number. You can count it. Just like you could count how many atoms you have. It'll be a big number, but you could count it. Even though people can be any shape. You know. In other words, the photon is like the atom for light. We can investigate further. Continue it. So actually we should think about electromagnetic radiation as a group of photons. Now you notice I've deliberately not used the word wave or particles of photons. It's a group of photons, whatever a photon might be. Okay, so you can have some distance, and then you can have a smaller distance, an even smaller distance, even smaller, smallest. Okay, so just to be clear, you can have some light wave, a smaller light wave, an even smaller one, an even smaller, but then you have the smallest one, which is a photon, and then anything less than that, there's no light wave. Okay, so we're clear on what a photon is. It's the minimum light wave at the moment. Thus, a photon of light is like an atom of light. Okay. So what is a photon? A photon is a particle of light. That is a single quanta of light.
Then it's a particle moving.
It's a particle of light that behaves like a wave. But it's a particle of light that behaves like a wave. But we'll worry about that later. Although you probably know all about this from your active listening. Exactly.
Why do you use quanta? You say it is plural, but a single quanta.
Yeah, maybe there should be a single quantum of light. I'll have to check my grammar. A single. I wonder if I mixed up quanta and quantum.
Quanta sounds more like single.
Yeah.
Doesn't it? Maybe I have it backwards. Quanta, one quanta, two quanta. I'd say you're right, maybe I have it backwards. What? You think it's the right way around? It doesn't matter. You're not going to get quizzed on your grammar in the physics exam. If you write quanta or quantum, who cares? Yeah, but it doesn't matter for your marks in physics, so it's all good. Okay, continuing. So, it was Einstein who discovered the light photon. In fact, this is what he won the prize for. Oh, Jerry and Sean, you're not listening to me. Okay, Sean, you're not listening to me. I said, Einstein discovered the light photon. And in fact, this is what he won the Nobel Prize for. He did not win it for E equals mc squared. He won it because he discovered the photon.
Yes.
Yes. Thank you. He also discovered that the energy depends on the frequency of the wave. Now, this, if you really think about it, is quite surprising. Because if you think about a wave hitting a boat, what do you think is the most important thing about the wave if you want to know how much energy the wave is hitting the boat? The amplitude, yeah. A big wave is worse than a small wave if it hits your boat. It imparts more energy. So you might think it's the amplitude that says what the photon's energy is, but in fact it's not. It's the frequency. And this is why X-rays and ultraviolet and gamma are harmful, because they have a lot of energy, because their frequency is high. So Einstein discovered, in fact, it's the frequency that matters for the energy of photons, not the amplitude, which seems a little bit strange.
The amplitude can be lower than pulsation.
Yeah, which would impart a lot of energy when it strikes. So like a UV ray, even one with low amplitude, if it has a high frequency, then that would have a lot of energy because of the frequency. You know, so that is, the higher the frequency, the higher the energy. And in fact, Einstein has a formula, Einstein has a formula for the energy. It's very simple. If you want to know the energy of the photon, you just take its frequency and multiply it by Planck's constant. And Planck's constant is quite a small number. There it is there. 6.626 10 to the minus 34 joule seconds.
Why is Einstein so clever?
Yeah, he did discover a few things, didn't he?
It's actually 200.
Could be. Nearly as much as mine. Huh? What do you mean? Oh yeah, well, you know, people suck. So, indeed. Okay. So this constant was discovered around about 1901, perhaps. This is Planck's constant. But Einstein saw that you can actually use this constant to calculate the energy of a photon by knowing its frequency. In fact, you used to calculate this in chemistry, but I think they took it off the course. There used to be a section in chemistry called quantization, perhaps, where they studied this in chemistry, the frequency of the photons, but you don't do it anymore. Okay, you got this formula? It's a very simple formula, very simple. Here's a very simple question I want you to tell me. A photon of red light has a wavelength of 400 nanometers. Firstly, what is the frequency? Okay, so what formula gives you the frequency here?
Yeah.
No. V equals lambda f. And what's the V here? It's like C. So C equals lambda f. Okay, so calculate the f for me, please. You got it, Sean? What's wrong, Lee? What could possibly be wrong? You just have to divide two numbers.
This discovery is like centuries before.
What discovery?
Einstein discovery.
Oh, a century ago.
Yeah, and I mean those times they have no like advanced technology to prove anything. Why does science like today cannot?
I know, kind of sucks, doesn't it? To prove anything now, you need a 20 billion euro Large Hadron Collider. Yeah, the days of the pendulum are long gone. Yeah.
What is the end?
Yeah. Back in the day when you could use a pendulum to prove stuff.
What is this?
Not anymore.
I mean, how can no one like because they want to prove him wrong?
Because he was right.
This is
Do we have a frequency, Sean? What is it?
7.5
Yeah?
power 10
14?
plus.
What did you get?
14.
7 point?
5.
I trust them. I trust them. Okay, next part. How much energy does this photon have?
H.
Yeah, just multiply your last answer by H, please. What did you get? Yeah. Sean!
490 is 90.
Small amount, isn't it? Small amount. So what would be a more appropriate unit? EV. So how much does this have in EVs? So take your number and divide it by E now.
EV, but
Teacher, how do you connect it?
It's not a Pokemon.
Oh, yeah.
Yeah.
Thank
By
you
the way,
for knowing.
Jolteon rock.
Yeah, how do you connect the A? Me?
Calculate the A.
Light of speed
Oh.
divided by wavelength.
This one, Jerry.
We know A.
Yeah.
We know lambda.
Yeah.
Gas.
Thank you, Sean.
So why we?
So simple, so clear.
No, I told you.
Unlucky.
409.
Ah. It's 400 multiplied 10 to the power by 10.
Yeah.
Right, what is it in electron volts?
3.1.
3.1 electron volts. More reasonable unit to be using. Okay, continue. So it's easy at the start with. That would be like a section A question, except of course they wouldn't give you the parts. The section A question would just be, a photon of red light has wavelength 400 nanometers. What is its energy in electron volts? So first you need the frequency, then you need the energy, then you need it in electron volts. Simple enough question. Right, here's another interesting one. Your mobile phone uses a frequency of about 900 megahertz. Okay, so your phone here, the frequency of the wave that's coming out of this is 900 megahertz. And the power output is about 4 watts, meaning every second 4 joules of energy come out in this form. Now it's not really 4 because some of the energy is used to make the screen light up and all this stuff. Like maybe on my phone it could be 4, but on your phone a lot of it would go to the screen, okay? How many photons come out of your phone every second?
4.
No.
Oh, photon.
Okay, so how would we do this one? So let's just think about the steps here. So we know in 1 second
4 joules.
we get 4 joules. Okay, so the energy will equal to 4.
Yeah.
Fine. Now, this is wrong.
Huh?
Why should I not say this? Why is that wrong? No?
Because it's the battery, not the proton.
That's energy output.
No.
Because it is not 100% efficient.
No, because there are many photons. Each one of them has a frequency. Basically, we have to put an N here because it's for all the photons. Okay, so do we know N? No. In fact, N is what we want. So N equals 4 over HS. Now, do we know F?
Yeah.
We do actually because it's 900 mega. So times 900 times 10 to the 6.
Oh yeah.
So if we put this in on the calculator, quite simply we can get the answer, which should be a big number.
Divided by electron.
No, because I want to know how many.
6.7.
Yeah. Okay. Every second, that's how many photons hit your face when you're talking on the phone.
Yeah, it's radiation.
When
Is it radiation? I don't know. I'm just saying.
Yeah, but the wave only comes out when you're actually in a call. So, the connection with the radio tower. The electromagnetic wave is only active when there's a call going on. Otherwise, it's not. When you're in a call. No, there shouldn't really be any photons coming out of that.
There's light.
Photons to the electromagnetic, obviously from the screen, yes, but you must remember when I was writing this question, I was thinking of a phone like this that doesn't really have a screen, okay? That's okay, that is okay.
Is
Yes.
it harmful if we get more frequency?
No, because remember, it's only harmful once the frequency goes past ultraviolet, and 900 is not ultraviolet.
Can you put more frequency there?
Higher frequency? Yeah. That will be harmful.
Because of photons.
The photons will have so much energy, they damage the cells when they impact it.
Is this why sometimes we play like video games for too long, we get hot on face?
No.
Really?
No.
And because you watch some secret.
No, seriously, like when you play
Yeah,
games.
just you.
No, when you play games, you got hard.
Go on website.
You are using the phone to control on the game.
Okay,
You're flipping yourself.
Oh,
Okay, he's watching.
give me strength.
Seriously.
Okay, can you finish trolling him and can you just be quiet, please? Right, continuous. So to answer your question, it's not harmful because the frequency is not in the dangerous range. Simple as that.
Oh, then
Yeah.
if frequency is high, then because of photons, it is harmful.
Yeah. Photons only become harmful when their frequency is in the ultraviolet range.
Teacher.
This frequency is actually quite low. You know, it's lower than visible light.
Teacher, you said even the, I mean, you did mention before, even the frequency is not harmful, but if there's like large amount, it can be harmful.
No, not even that.
Just have a.
Just depends on the frequency.
Is that over the frequency?
Yeah.
Even
A small amount, yeah.
can hurt.
Yeah. If it's less than the frequency, if you have lots of photons, the worst it will do is just produce regular heat. Whereas if the frequency is high enough, yeah, but not from, like, I mean, when I say a lot, I mean, 1,000 times more powerful than this. 4 watts isn't going to heat it up. You have enough of it, it'll produce heat. But it's just regular heat, like heat from a fire. It's not damaging heat like radiation burns.
Is it the electric stove using the kind of
No,
the microwave oven would use a process like this, because remember, when we looked at the microwave oven, it produces a standing wave. What's happening is the frequency is the same as the frequency of water, so it resonates the water in the food. Same thing can happen with your skin. If the right frequency hits it, it'll resonate with the water in your skin, and this will warm it up. Yeah, but it's not because of radiation poisoning. It will have the same effect if I throw you on a fire. FYI. Okay, continuing. Now, electrons on the surface of a metal are trapped. They require energy to be freed. So, if you have a piece of metal, there's electrons in it.
that is not true. What we learn in chemistry is the electrons in the matter is free.
Yeah, no, but when I say trapped, I mean trapped to the metal, in that they don't fall off the metal. They're freely moving around the metal, perhaps, but when I say trapped, I mean they're trapped to stay within the metal, although they are free to move around it. The difference is prisoners could be free to move around the prison, but we could still also say that they're trapped within the prison. So it's the same thing here. Therefore, they have a negative potential energy. If you want to take the electron away from the metal, it requires energy. So remember, we said if it's trapped, it has a negative potential. The energy you need to free the electron is called the work function. So the idea is the work function phi is the minimum energy needed to remove an electron from a solid to a point outside the solid. So this is our solid, there's an electron on it, and if I want to remove the electron, the energy I need is called the work function. This is a lot like the ionization energy level. In fact, really, it is the same thing as the ionization. Yeah. The only difference is the context. When we talk about ionization, we usually are talking about a gas, whereas when we talk about work function, we're usually talking about a solid, particularly a solid metal. Oh yeah, because it's always trapped to the metal surface.
Can you calculate how many photon is coming from the
Very good. Yeah. Because you just need to know the energy per square meter. No, you could definitely work it out. I remember this being a physics question at university. You could definitely work it out. We know the distance we are from the sun. You would need to know that. You would need to know the energy per square meter on the surface of the Earth, and we know that. If you put the two together, you can know how much energy comes out of the sun per second, and divide it by the h and the frequency, and you've got the number. Right? I don't remember the distance, but I think the energy is 100 watts per square meter. Okay, continue.
Yes.
Right. Now, when a photon strikes a clean metal surface, it will cause the release of electrons from the metal surface. So, if you have a metal and there's an electron trapped, when the photon hits the electron, it can give it energy and free it. This only happens if the photon has enough energy. If it doesn't have enough energy, then it can't free the electron, obviously. This process is called the photoelectric effect. When you free an electron by using a photon, that is called the photoelectric effect, discovered by Einstein.
Again?
I know! Yeah, he's physics Jesus if you want, I don't know. He discovered Brownian motion, but it's named after Brown because, Einstein already had enough named after him. And he also was the first person to calculate Avogadro's constant, but it's called Avogadro's constant, not Einstein's constant, so Yeah. And his original estimate of Avogadro's constant was quite close. Like, he estimated 6 times 10 to the 23, whereas the accurate value is 6.02. And you got to remember, he was doing this using a microscope and pollen from a flower. I'm sure there's some tricks you can do, but essentially he was looking at the movement of pollen under a microscope. I know, this is what you had to do back in the day. Oh yeah, something not right there. Alright, continuing.
No, not yet.
So what do you mean by clean metal?
Yeah, the metal surface really has to be clean, but there's no dirt on it. Yeah.
Okay.
You don't know what clean is?
No, I know, but why?
Why does it matter? Yeah, because if it's dirty, when the electron is freed, it will hit the dirt on the surface and bounce back in. Yeah. Yep, you remember the symbol for that now, don't you? The double arrow, yeah. Okay, continue. So, the reverse is true. So what I mean by the reverse, because the if and only if means reverse is true. So, if you have a photon, Jerry and Sean, are you listening to me now? You're making me angry. No. Me, I'm your dictionary. Okay. So, if you have a metal, and there's an electron here, you can send a photon in, hits the electron, and the electron is freed. The opposite is true. You can take an electron and fire it to the metal, it can stick to the metal, and release a photon.
the light.
The light, yeah. Yeah. It can go both directions.
But is it like more durable?
That's the one.
Stop now. So this is important in chemistry, but it's good to know that it goes both directions. That's why I say the if and only if. Okay?
So is photon considered a negative charge? That's why it repels?
No. What's happening is the electron has negative potential and the photon has energy. We know the formula, HF. And when it hits the electron and is destroyed, the energy is given to the electron and it can release it. Yeah, well, maybe not destroyed, rather I should say absorbed. Yeah.
If electron go out, then can it be like same in materials?
What do you mean?
Like if charge is different.
Oh yeah, I understand what you mean there. Because it's lost an electron, it loses a negative charge. Yeah, that's true. So I suppose now its charge is increased by +1 the metal surface. That is true. And in fact,
only one electron.
Well, if one photon hits one electron, then it makes it +1. And in fact, that is how solar panels work on your calculator. So you see this calculator here. What's happening is the photon hits the metal surface and frees an electron, and this freed electron then is moved around in the circuit. Yeah. So in fact, solar panels are very simple to make. You just need a clean, shiny metal and to put it into a vacuum so that when the electron is freed, it's not crashing into anything. You can pass it through a conductor. Yeah, isn't it? It's very, very simple, the solar panels. It's just, now there's other types of solar panels, but the simplest solar panel is just a clean metal.
Why is it so?
In a vacuum, yeah. Huh?
Why is it not so, how can I say, the energy generation? Like oil or something like that?
The problem is the electron has a negative potential. So when the photon hits it and gives it energy, not all of the energy from the sun is turned into electrical energy. Some of it is used to free the electron. So this is kind of wasted because you want the electron to be freed easily and get moving in the current in the conductor, you know. So to make a good solar panel, it needs to have a small work function. The electrons need to be easily freed. I said if the photon hits the electron, it frees it. If it has more energy than is necessary, what do you think will happen to the electron? When it's freed, it will be moving faster. The extra energy is turned into kinetic. Okay? The work function is wasted energy. That's why the solar panels aren't as efficient as you think, you know. Maybe for every 100 joules, maybe 80 joules are wasted to free the electron, and 20 joules are actually electrical energy. Still the same. Yeah, but I mean, it's still the same problem we talked about. It's hard to store green energy, you know. But there's other ways to do solar panels, like Jerry was saying about using mirrors. You can actually just use mirrors to focus the light to heat up some water. That works too.
No mirror, I mean kind of a mirror. I mean the opposite kind of reflecting.
Yeah. There's many ways to do it. Many ways. Okay. So the reverse is true. Right. Here's just a little table here. Low frequency and low intensity. So just be careful about the difference here between frequency and intensity. Okay. Frequency, you know, is like the color. Like the speed here. The high frequency would be like ultraviolet, gamma, X-ray, and low frequency would be infrared, radio, Wi-Fi. This is low frequency. Okay. Intensity is how bright, which just means how many photons really. You know, if that light is bright, it's only because there's more photons, not because the frequency is different. Because the frequency is the color. The intensity is just how many photons. Okay? So if you have low frequency and low intensity, do you think that will free many electrons or not many electrons? What do you think? Well, low frequency means that it won't maybe free any electrons. So you would have some freed electrons, maybe. but they would have low kinetic energy. And yeah, that's really it. Now, high frequency and low intensity. Well, the high frequency means the electrons will be freed and they'll be moving fast. But because there's low intensity, it means there's not many photons, so maybe not as many will be freed, yeah. So, some freed electrons, but they will have high kinetic energy. Okay, what about this one? Low frequency and high intensity. So that means the electrons will be freed, but they won't have much energy, but because there's high intensity, there's lots of photons, so there's lots of them freed. So many of them are freed, but with low kinetic energy. Yeah. So many freed electrons of low kinetic energy. And lastly, high frequency and high energy, well, it's obvious now, what is it? Many freed electrons of high kinetic energy. So I would like you to copy this table down, please. And then I think we'll finish on that, will be good.
So when electrons free then remain in circuit,
Yeah.
is there any like limitation of free electrons? Is it the number of particles?
Oh yeah, like how many electrons could you free? I mean, the number of electrons in a piece of metal is so huge, and you actually don't need to free.
Is it like multiplying by more multiplied by
It's a huge number, yeah. And also the electrons re-enter the metal surface, I think. So like when the light hits the metal plate and frees the electron and moves in the circuit, it will just attach to the other end of the metal at the back of the circuit. So I don't even think the electrons leave the circuit. So I suppose in theory this process could continue. Because the metal is in a vacuum, it won't oxidize. You've done oxidization, yeah. And you know, when metals are in air, they oxidize. So this is in a vacuum, it won't oxidize. So it could actually continue for a very long time. I think the copper in the circuit would oxidize before the solar panel would. No, I don't know, that circuit is stupid, don't draw it please, I don't know. I don't know why I felt like I had to put something there, but it's actually a stupid circuit. I shouldn't have the light bulb in it, or there's many things wrong with that, please ignore it. I think I just googled photoelectric effect and took the first image without thinking, no problem. Did you write the table down? Then you can go.
What was the question?
Well, there's still more slides to do. But you can see it's not too difficult. It's really just one formula so far, HF. Again, this is another reason why I like atoms in the exam. I mean, the formula is HF E equals MC squared. Has there been any other formulas in atoms? Oh yeah, the exponentials, yeah. But they're very similar to the electricity capacitor formulas. Oh my goodness. What the heck is that? Is that your phone or mine? It must have been yours. No, I have intake 2 now. Ah, that's okay. They're nicer group than this group, so it's fine.
What?
What? Was there what? Oh, no, he didn't. What? Huh? About what? Oh, those two. Ah, they're all right. I mean, they're not as bad as, you know, Lee or Andrew.
Oh, Andrew. Nice is forgetful. It's
Huh?
easy to forget.
What's forgetful?
Nice.
Nice.
Yeah, begin nice. It's easy to be forgot.
It's easy to forget to be nice. Is that what you're saying?
A nice person is easy to forget.
Oh, they're forgettable.
It be forgot by others.
Yeah, yeah. A nice person is forgettable.
Yeah. Yeah, forgettable.
But a Lee is unforgettable.
Yeah, unforgettable.
Is it not?
Everyone is nice, yeah.
Hang on, do you know what a synonym for Lee is? An Andrew. You know synonyms? Yeah. You have a Lee or you can have an Andrew.
Andrew. That's a compliment for me.
I am the synonym of weird.
Bye bye.
True that.